waiting for the traffic, gets the traffic, does work, sends a response back. Oftentimes the box will also do like batch jobs, but you have one machine that can do a lot of things. For example, I have one machine right now, and it runs all of my personal domains, which is like, I think it's like 21 applications plus a database, plus kind of classic Linux processes like cron, doing work, and that's fine. None of my websites get a lot of traffic, so as long as like the machine doesn't disappear, everything's okay. But there are there's a few more downsides than just the machine disappearing. Common issues, obviously, like, hey, let's say one of my websites gets really popular, and then that binary, let's say in this case most of my binaries are like Ruby processes, will take over the entire CPU. I only have 2 cores in this machine, so I can only handle so much traffic. Also, a classic problem, I use Google Compute Engine, but AWS and like every other hosting service has this problem where if your data center goes down, your VM goes down, and when all of your stuff is hosted on one machine, everything disappears. This is becoming less of an issue now that we have like the cloud, but how big, like essentially how fast I can grow while sticking to one machine is just straight up correlated with how much money I have. This used to be the classic like let's throw money at it solution to like all scaling problems, where it's like, well, we've got this one box, it's doing the job, why don't we just put in a bigger hard drive, or put in more RAM, buy a new CPU. And as like an individual or like an ops person, you kind of have to make that call. Is it cheaper to just upgrade the RAM or work on starting to split that into multiple machines? And so it's kind of where you get to make the technical decision to scale. So the example I'm going to give is ifixit.com, which I worked at for 2 years and is in town here. But you have to, at some point, when you're building any sort of application, you go from like queries per day, it's like, hey, I'm getting like 5 individual users every day, to like, oh hey, I'm getting like 5 queries per second. Like, okay, like that's just more significant. You're like, oh, I'm getting like 30 queries per second or like 100 queries per second. Like, now this entire machine is devoted to running this one process. And like, now my database can't run, or I never optimize my database queries, and when I hit the server for this one page, then my entire website just halts for everyone else who sent a request because the entire CPU is taken up doing processing on this database process. So this is iFixit's architecture as of 2010. Kind of see here we have load balancers. iFixit in 2010, I think this was like March 2010, was running 2 websites, ifixit.com and makeprojects.com. And the DNS was set up pretty simple. If you hit ifixit.com, you go to this load balancer. If you hit makeprojects.com, you go to this load balancer. And then they'd send the requests to an array of application servers. Basically, one request would say like, hey, I need this web page passing down the path, and I need it for ifixit.com. While make would send it and say like, I need it for makeprojects.com. And that would trigger like some slightly different logic, and you get different CSS, and you'd be like, yay, pretty pictures. And when those apps get the request, what they're actually doing is going and talking to a master database of MySQL, which also has a backup slave database. Can you guys see like any problems with this architecture? Yes, no, maybe?
The database?
Yeah! So, what happens if this disappears? Just wild guesses. Yeah, bad. Like, basically, if your master database disappears, then all of these app machines can't do any database work. And the majority of web apps, most of the actual data is stored in your database. So kind of the first step when dealing with that is create a slave database. And so what a slave does, at least in MySQL, and this is totally dependent on whatever database system you're using, is you set up basically binary logs. And so this stream is a constant stream. Whenever someone commits data to this database, the slave is doing the same exact command, or the same exact write command. So we can actually, if this disappears, which happens, for instance, this used to be run, it probably still is, on a AWS instance, and AWS doesn't promise that it won't delete your VMs. Exactly, I don't think any cloud provider promises that. So they just, that machine disappeared. And so what we can do is say, hey, all application machines promote the slave to a master. So stop trying to read logs from this other machine. And now, whenever you do requests, send your request to master. And then while we also do that, we bring up a new slave, which then slowly downloads all of the log history to master. And so that's like a solved problem in that given you see the database disappearing, you can go and run like a few commands to switch over to your master and then wait like an hour to have a new slave, which is all kinds of problematic. And then also we've got this like cloud over here of app servers. So iFixit always had one app server because no matter what, we're always going to have requests. But iFixit had this problem has this problem where certain days of the year, basically when new gadgets come out, iFixit goes from 300 QPS to 3 million QPS. And so what you need to do is grow this array of machines. You need to tell the load balancers, hey, I now have 10 machines instead of 3, and usually you increase cache timeouts on both the load balancers to say hey, cache these requests and send users stale data because I really don't care if their data is 5 minutes old. I'd much rather not be hitting all of the app servers and the database constantly for a million times a second, especially if it's the same request. And you do that by monitoring and paying attention, but all of this is a very manual process. Oh hey, the iPhone 4 is coming out in 2 weeks. Make this a lot bigger. Make sure it still works when we have 10 machines. We haven't made any assumptions anywhere. And it's just kind of very manual process of growing everything. And I think the thing I forgot to mention is there's also memcache servers on both the load balancers caching all of those requests. It's not a magic thing. Now I'm going to pick up notes because I think I forgot something. Oh yeah, and also batch work, which I mentioned briefly in the single server side. You need somewhere to do the heavy computation. iFixit's big computational problem is they've got a lot of images, so they need 4 or 5 different resolutions. So they had basically batch jobs at the time on these 2 servers that would run and resize images and upload them to an external file storage. Yeah, common issues with this sort of scale, which is that's a pretty common architecture for a cloud-hosted internet service. Capacity planning, so basically knowing that, hey, we're going to get this spike. Some companies don't have that luxury. Oh, hey, we got featured in the New York Times, and here's a gigantic spike, and everything crashes and blows up. Network latency. You'll notice since the memcache servers were on the load balancers, if for some reason the connection between the app servers and the load balancers dies, you get all kinds of latency either setting that cache. So if 2 requests come in at the same time, they're both going to have to go to the app server because the first request can't set the cache fast enough for the second request to take advantage of it. DNS, you don't want to like do handwriting IPs for all that stuff, so you start basically using DNS to know where your servers are. So you have like app1 dot ifixit.com or whatever instead of 192.168.1.1. So you actually can like kind of remember where things are instead of, what was that IP again? Let me go find that random text file. Load balancing to make sure you don't send all of your requests to the first application machine, and regional outages, as I mentioned before. If all of your servers are in like an East Coast data center and there is a gigantic tornado typhoon thing that takes down the entire East Coast, kind of screwed. Yeah. So as you scale, you'll switch from having kind of, I guess in that picture you did kind of have specialized servers, but you slowly spread things out. So iFixit's first step was they moved database machines off of the application machines. But then you start getting things like, well, what if I have a single memcache server, or I start using some other caching system that lets me have essentially a global system that says, oh yeah, this machine has a cache for this large file. Dedicated hardware load balancers, instead of just running like HAProxy or Nginx on a front machine, you pay Amazon or you go and buy a physical hardware load balancer whose sole job is to make sure like queries get from point A to point B correctly and scale across all of your systems. Computation machines, groups like Wolfram Alpha, for example, they have huge, like all of their problems are in, given this query, what is the proper answer? And they can pre-compute some of that, but a lot of that stuff they also have to do on the fly. So then they, that's where they're scaling up these huge amounts of CPU. Distributed lock managers, which you don't really have to deal with when you're at like 10 machines, but once you get to like, say like Zynga has rumored 20,000 machines in the cloud. They need some sort of system to set the state across the entire like fleet. Whether that's saying like, hey, I have 20,000 machines, there's like 10,000 over in US West, there's like 5,000 in US East, and like another 10,000 across Europe. You need to be able to, you have some sort of system that can hold that. There's a ton of them. There's Zookeeper, which is Yahoo's, and it's open source in the Apache Foundation. Google has a paper on theirs, it's called Chubby. There's a bunch of others, but basically global locking system. And then like log servers, because you want to actually be able to find out what's going wrong. I spend a lot of my time using a tool called Dremel, where I actually go through and I look at like last week's logs, like what was the average latency from between like our network machines to our VMs. And oh look, there's a huge spike here in Atlanta. Why? And a lot of that is you tend to be like retroactive after seeing something really bad, either like bad press, like our first, Google Compute Engine and Google Cloud Storage is like early press, when they both were kind of like running at the same time, it was faster to get a file from S3 to Compute Engine than it was from Cloud Storage to Compute Engine, which is basically saying like it's faster to go to another company's data center and download a file than like walk next door and get the file, which is like all kinds of bad. For both like press and like, didn't think about that kind of scenarios. And so you gotta look in the logs, like what are the kind of requests that are happening? Like when the person did this, like what was going on? Maybe there was a fiber cut, like it's very possible they were making requests from Europe. And something bad happened and there was a fiber cut in New York. New York is the hub for like most transatlantic communications. So then like, I think there's 3 transatlantic cables, and so like if 1/3 of your transatlantic capacity is gone, like obviously you're going to see a some sort of problem, and especially if maybe S3 at the time was doing caching in Europe, and you're hitting like an edge cache in Europe. Those sort of things you got to like figure out what's actually going on here. So yeah, logging, huge. And this is also the time when you start doing config management. I mean, hopefully, actually, you can do that starting at like your first server, but you want to actually like check in your configs and make sure that like you have consistency across the entire fleet. while you're like one machine, yay, my one machine's consistent, right? Like, you only have one. But as soon as you have, 10, you'll start thinking like, hey, I should, check in all of my common configs, and I should make sure all of my machines are running the same versions of the same config. And then when you're at 20,000 or 100,000, like, everything must be the same, why, or otherwise, like, everything's breaking. Yeah, more common issues. So at that scale, you run into, like, you start having, like I said, tracking across the entire world. And a classic mistake that I've seen in, like, inside of Google, outside of Google, everywhere, is like, oh, hey, I have, like, database, it's pretty simple. I don't want to start dealing with scaling my database internationally. So I'm just going to keep 2 databases in, like, US, and I'm gonna scale everything else out. And then you, like, go up and you slap someone across the head. You're like, dude, everything still has to come back to the US. And so now you're basically adding, hundreds of milliseconds of time between, every time someone hits your site in Europe, and you have to go back. If it's not cached, you have to go back to the US, load up the data, send it back across. Yeah, it disturbs me how often I've seen that. And then, network latency. People kind of forget, like, when they're initially designing, like, your development system, yeah, everything's super fast. I don't see what the problem is. I get, like, 0.1 second, 10 millisecond load times, or all kinds of, like, crazy numbers. And then you deploy to 1,000 machines across the world, and they're not next to each other. And people are like, what do you mean I have more than, like, 25 milliseconds latency in between my machines? That's not acceptable. Like, well, deal with that. Caching, usually you start moving caching closer to your application servers or whatever it may be. Load balancing, once again, you don't want to send unless, so if someone sends in a request in Europe, you want to give them data from Europe, if you can. Obviously that's not always the case, but you want to try to have your load balancers take both region and load into account when sending people to where they're going. Once again, regional outages and config management. So yeah, Google. How do we go, like, what is the next step? Google, to an extent, is kind of all of those problems, but at, like, a 2 or 3 magnitude scale. Next picture. Oh, yeah. So Google has a lot of data centers and spends a lot of money on data centers. This was a quote on a website called Data Center Knowledge about our Q3 finances, which came out, like, at the end of Q3, which was like a few weeks ago. And basically, like, we spent what's considered, like, the largest amount of money on data centers ever. And that was just in 1 quarter, we spent 2.3 billion-ish on CapEx, which we then said in our financial report, it's all data centers. Which people are kind of excited about, because, like, yay, faster computing, more computers, and it also means, like, local jobs for wherever we're building data centers. So, like, the U.S. government scope, we're, like, bringing jobs to places like Iowa and, like, Oklahoma and places that don't necessarily get a lot of technology jobs, and also, like, more power usage. But it's also like, hey, we're investing in this cloud thing, and here's, more proof, and we're just scaling like crazy. In fact, as of, I think it was like Wednesday, this is our published list of external data centers, or Google data centers. You can see there's 13 spread across the world. A big chunk of them are in the Americas, but there's also some big ones in both Western Europe and Asia. One kind of funny thing you can think about is, like, getting network over here, just because of infrastructure problems, is really slow. And, like, your latency, like loading Gmail in, like, Australia or, like, India or Africa is a far worse experience than loading it, in Japan or loading it over in the US, just because you have to travel that network distance and the infrastructure isn't built up. And, like, a safe, Google doesn't publish our, like, numbers for, like, how many computers are in each of those. but let's say like a safe bet is like 100,000 machines per dot, like just in kind of your estimation math. Sometimes some of these are like way bigger than others. If you ever do like the Google satellite view, all of those, it's like google.com/operations. I've got the link and there's a reference page. You can click on the link and then like do a Google Maps satellite view, and you'll see like some are like one building, and then others are like 40 buildings. And you're like, oh, like I wonder if that one maybe has more machines than the other. And I was mentioning at the beginning, actually, Google did this kind of weird thing. They did PR with their data centers, which I didn't really understand initially why they did it, but it made a lot of really cool pictures. Wired went in to, I think it was 5 of our data centers. It was like Iowa, Belgium, Oregon, some other places. And like took pictures. I'm pretty sure this is Belgium because it looks very, very cold. And if it is, this used to be a old paper mill. And they've thrown like, oh hey, we can pump in a ton of seawater. We run our data centers like way hotter than most companies. And so this was one of the reasons we picked that is we can take like cold seawater in and use that to help cool the entire building. This is another data center. This is a like long array. These are all cooling towers. Maybe you can kind of see pictures of cooling towers. And it's kind of like the big cooling tower that's like over there. You guys know what I'm talking about? But on a much larger scale for this, entire. Actually, looks like it's 2 buildings. It's kind of like wrapping all the way because they got to cool down the stuff they're piping through all these buildings. Another, you can see, like this is actually. This may even be like more than 3 buildings. So there's like. You have data center there, data center there, data center there. Looks like there's another data center over here. Probably pulling off water off that river. Huge cooling towers. This is a farm of generators in case power goes out, because that happens. Yeah. More cooling towers. More cooling towers. Satellite uplink. These, as far as I know, aren't used too often because satellite is much slower than wired. And Google runs a large amount of connections between all of our data centers. So it's kind of like if you enter at one data center, you won't hit the public internet until you can easily go from, like if I come in Belgium and I need to actually go over to Iowa or something, I go through Google's encrypted network all the way over to Iowa and then back out in Belgium. So a lot of times if like one data center's out, we want like backups to do sort of emergency communications and stuff. Racks, lots and lots of racks. These are all, I think these are all like index machines. So these are all machines that don't have like any local disk or like very little local disks. They're probably all just like doing large amounts of computation. These are racks without computers in them, which is kind of cool. So you can kind of see there's cooling and networking here, and there's like cable runs to run the cables between all of these different boxes. And then you've got like power runs, and then there's cooling lines and lighting. And this is kind of like before we filled it all out. This is sort of in the middle of the building's process. More pictures of racks with pretty lights on them. One kind of thing that I found very interesting looking at this photo, which I guess makes a lot of sense, but when you get to this scale, instead of, like I was talking earlier about config management, right? You maintain like a database of all of your configs or the application. This, we have to maintain a database of like every single machine. So every single one of these has barcode. In fact, they probably have a few barcodes for the different parts that are shoved into them. And you'll notice they also don't look like your traditional rack servers. They don't look like a fancy black box you buy from like Dell or something. These are essentially like a flat sheet of metal and like motherboards and like other things kind of just strapped onto it in a very organized and professional fashion. But like when I look at this, I'm just like, oh, so they just kind of threw some stuff on board, plugged it in, and like, yay. that being said, we hire like, I don't know how many, but a lot of mechanical engineers that do a lot of this work. And once again, most racks don't glow blue and yellow. That is a post-processing. More racks, a friendly hardware operations guy who actually like goes and maintains these servers. One kind of interesting thing about Google is we have 45,000 employees as of whenever Q3 ended, and most of them have never been in a data center. Like myself, I've never been inside a Google data center, and until these pictures were released, I had like ideas of what a data center looked like. I've like walked into smaller ones, but the majority of my work is all via remote. So I sit at my desk, I run commands, I say like, hey, I need 10,000 servers set up with this configuration in Belgium. Like, hit the script, watch a graph. Like, and I spent time and I coded that script and I made sure that like the graph was going to actually output the right stuff. But I'm not going into the data center and sitting down and like, all right, rack this machine, plug in a terminal, run the script, move on. This all happens remotely. The only thing that happens actually locally is there's a team in each data center, as would make a lot of sense, that pays attention to like, hey, we're having network connectivity issues on like, rack 13B or something like that. Dude, scrolls over and like, what's wrong? Oh, this battery's busted, or something like that. And hopefully our monitoring, it's usually set up so we monitor like everything. So he actually knows specifically what's wrong, but he can go over and rip that machine out and replace it. More pretty pictures of racks. And cool quote. I guess I should. So, do you guys have any questions about like all those pictures that just kind of flew by? No. John Alspa he actually came and spoke here, like in '07, I think. And he's kind of like one of those famous programming guys. But instead of like being famous for like building a really cool company or anything, he was known as the guy who helped Flickr scale. So he was head of Flickr operations for many years, and then he left. I think he's the CTO or VP of operations or something like that. Somebody important over at Etsy, and he kind of helped them go through the same sort of problems. And he has this quote: "Web applications can fail in all sorts of dramatic ways, and you're not going to foresee all of them. What you can do, however, is make use of what you do know about what happens in your real world on a regular basis." So this is kind of, I guess, the like age-old like Boy Scout motto: "Be prepared." But it's like more of like be super paranoid and watch like everything. So we at Google have a team for that. SRE, site reliability engineers. SREs are what I would describe as like the most paranoid people you'll ever meet in like the computer world. They try to be like a semi-happy bunch, but like when you're interacting with them as like a software engineer, and you're like, hey, I want to release this cool new application, and they look at it and be like, no. And a lot of that is because they try to act as like the paranoid parent of Google. They spend 50% of their time on operations and 50% of their time on engineering. We use the same exact tools as developers. I spend most of my days like writing Python, Go, a little bit of Java, and like reading C++ because I still don't know how to write it. We do unit tests. Google every piece of code that's checked in, whether it's a config, a shell script, or Java application, or a kernel binary or a kernel patch. All has to go through peer review. We follow like very strict coding standards. Basically, there are people inside the company that are gifted as people who have readability, and they are the people who say like, this code can be committed, this is like valid Java, or like this is valid Go, or this is valid C++, to keep a consistent style across the entire company, and also a like certain level of quality. Those are the kind of people who are like, hey, like there's no tests on this. And you're like, hey, I'll get back to them later. Like, no, there's no tests on this. And all of our configuration is treated as code. So, let's say I have monitoring configuration. All of my monitoring configuration has unit tests. I have an alerting system, so I go on call, it's like 1 week every 2 months. And when I'm on call, I have a system that alerts me if monitoring reaches certain levels, right? Like if network latency is too high, I get a phone call. If all of a sudden VMs are disappearing all over the place, I get a phone call. Things that I can do something about that are broken, I get a phone call. And so we have to have tests to make sure that not only is the monitoring tested, but that the alert system's tested. And it's that kind of, when you're thinking that's just kind of tedious, but at the same time, you're paranoid because what if that alert didn't fire when I was on call? Then A, why'd you write an alerting system that doesn't alert you when things are wrong, you idiot? And B, oh hey look, we just there's this huge PR fiasco because Google.com's thing, right? Which, there's a very small subset of SRE that works specifically on search, and so I'm not responsible for Google.com, but could be the case. And we follow the same kind of develop, test, release, iterate process that most of Google does, and we write a lot of documentation. And kind of I guess our big thing, we learn lessons, continue to improve, that I hadn't seen before, but I think is really awesome, is postmortems. So let's say I'm on call, and something really bad happens. On the in the you're not going to foresee all of them category of problems. That happens. Somehow, for some reason, every 4 hours, 5 machines would restart and reset and drop all customer data off of them, and everything would go bad. Didn't have no alerts fired or anything, and what happened? I figure it out first. At some point, someone actually notices, then we go down and figure out, oh, this change I submitted a month ago was slowly rolling out to this weird load balancing system. It was slowly restarting a bunch of machines, but really slowly, so you didn't notice. So I have to write a postmortem once I fix things. And the postmortem idea is very simple. You write this is what happened. This is the timeline. A lot of times it's copy and paste of IRC logs, chat history, and emails. And you're Bob noticed that these machines were restarting, and then the process to fix it, and then also before that you add in Nat committed change X on Y, and so you have this entire history of what happened, and then you kind of have a what went wrong, what worked well, and then what are the things we're going to do to make sure this never ever 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 happens again. And those are very actionable things, right? You don't want just to be hey, we should monitor this thing better. You try to make sure that all of those are very action item things. So I could sit down, I could look at a line add monitoring for X and alert when Y. And that's something that I can easily sit down and be hey, I can punch that out. And then I guess these are bullet points from the guy I'm going to be working for in London. We work sort of slightly differently than SREs in terms of how our work is distributed. Or I'm sorry, SREs work differently than software engineers because a lot of our goals are sort of on a shorter time or a longer timeline. So we can't really do sprints, right? Or sort of the classic project management workflows, because I'm blocked on a new data center coming up in Chile, right? They're building this big new data center, and that's going to take 2 years. I can prepare for that. I know we're going to be in Chile in a year and a half, and I can get ready for that. But that's just on my to-do eventually. And if machines arrive, then I gotta pick up that work and go do it. So I just have kind of a constant list of projects that I can work on, which is nice because last night I had a little downtime and I was oh, I took off early on Friday. I should finish something. And looked at my bug. I was oh, okay, here's something that I can pound out in a few minutes. And it's very ad hoc compared to a lot of the, I guess, kind of classic, not even classic, but larger scale software engineering solutions for organizing work. So any questions about like SRE before I like start diving into like how Google scales, I guess? Okay. So the next two slides are actually from like a SRE, it's like a training doc. And sort of when we're scaling, we try to, or when we're like thinking about systems, sort of, I get a design doc in email that says like, hey, I want to build this new thing. What do I like, critiquing on it, basically. This is like early documentation before the software is being written. It's kind of a document describing what I'm going to build. And a very like technical, kind of like technical to the extent of like, I'm not like no code, but everything else before that. I'm going to use these systems. I want to be in these places when this happens. I'm going to do this. And we follow kind of two things, limiting factors and failure modes. So limiting factors are like, when I look at your application, what are the things that I'm not going to be able to grow? If you say like, this data store has to always be here, or has to always be up. That is like an obvious limiting factor. If I take away X, what's going to happen? Failure modes are kind of, or I guess failure modes is more of the like, what happens when I take away X? But how, limiting factors is more like, how do I scale the thing? But yeah, so we go through the doc and critique it on sort of those two levels. And so we follow, I guess, we take those sort of two rules and apply them to these 10 principles. This is like the best case if you're following the documentation, doing your job right. So keep servers simple. How many of you guys have ever heard of like Unix philosophy? Anyone? Yes, no? All right, so the Unix philosophy, it's like super old, you should look it up on Wikipedia, really interesting. But basically the idea is every application should be super simple and have similar interfaces. So you can kind of look at like cat, right? Cat takes in, it works on standard in and standard out for a list of files. And you can take cat and you can pipe it to a bunch of other Unix applications like sort or unique or anything, ls, and they will then do their thing, taking in standard in, outputting the standard out. So you can scale it up and think about servers. And when they say servers here, they don't mean like a box. They mean an application running on a box. So the idea being you should keep like your individual jobs simple. You should be building cat, not Microsoft Word. You build a lot of applications that work together to provide similar functionality of Microsoft Word. We have, an example is like Google Docs probably has a front-end server, and that's like front-end server's sole job is to serve like CSS, JavaScript, and deal with like user interactions. They probably have another server that deals with like commenting on Google Docs. They probably have a server that deals with actually storing the documents, and serving like read-only mode and stuff like that. So you have smaller applications that can all kind of work together. And this is great because each server can then look for any other, a running smaller server somewhere else. So instead of having to scale, 10,000 really big things, you can have 10,000 kind of small things, and they can be sort of scattered around across a wider variety of machines. Which is kind of point number 2 is these jobs should be like physically smaller, just kind of like the classic bin packing problem. You can fit more things into a bucket if they're smaller. And they should be stateless. So if I kill one of your little servers, it should be totally okay that you have like 50 others somewhere else, and it can just send that request to the thing. Which is kind of number 3, retry safely. So if you send a request to another one of these smaller servers, let's say your front end's like, hey, store this document to the back end. If that doesn't succeed, that should totally be okay. In that you should be able to send that same exact request to another back end and the back end should be like, oh yeah, sure, I can save this. Or you can see like, actually I see that the other back end is working on this, don't worry about it. And it'll just drop that request. And that's kind of, I guess, numbers both like 4 and 5 is you should bound resource usage and fail gracefully and don't crash, assert, exit on exceptions. So if you get a request and that request like basically makes your entire binary crash, then your job should stay alive. It's better to not return a good response for one user than start failing for all users across the board. And same thing is if we get DOSed or like start getting hundreds of millions of requests, we should have a limit where we say like, hey, stop, I'm busy. Like, don't send me anything else. Please, dear God, stop. And and you can tell a little about like stop sending stuff to you. And then you'll fail gracefully for those requests. You should be transparent, kind of like if as an SRE I should be able to go to any server running inside of Google and know what's going on. There should be like relatively obvious monitoring. There should be pages when I look at this job, like I should know like, yay, or oh god. And for the most part, anyone should be able to do that because you want to, I guess, is considered like increase your bus factor. There shouldn't be like only one guy with the password to all of your servers, because if he gets run over by a bus, then you're screwed. So instead, this is giving everyone the opportunity. If something's down, you can cover for that person, or you can go and fix the thing in case of problems. Thank you. So avoid lazy initialization. This is kind of, I guess, a hot topic among some people, but at Google, we pre-initialize everything. That way we know that if something's going to fail, it's going to fail up front. So that way you can sort of do what considered number 8 is canarying and very slow rollout. So I can roll out my new version, version 2000 of this new fancy program, and I roll it out to one machine. And I canary it, and it's like, all right, run. Is anything gonna break? No. You sure? Okay. I'm gonna then roll out to like an entire rack. So now I'm running like 40 copies of this machine, this program, and it's like, all right, we can all talk to each other. Everything's okay. And I sort of follow an exponential rollout. So next I may do like an entire like wing of a data center, and then I might do an entire data center, and then I might do all of the US, and then I might do everywhere. So kind of slowly scaling up as I roll out, and at any point in that scale, if I see the like, oh dear God, everything's broken, what have we done? Like, why didn't we test this? I can still go like, roll it all back before we get to the new version is affecting everyone. So then, 0.001% of my users got a like bad version of Gmail instead of everyone getting the bad version of Gmail everywhere, and we're on the front page of like New York Times or whatever. Anticipate the future, basically like monitor everything, please. And capacity plan, which is kind of a hard, there's books about capacity planning, but basically like if your graph's going to the right, like plan on having more resources, so when the graph keeps going to the right, you're not like out of resources. And check the user experience. I'll quote here somewhere. But basically, we at one point, I think the search slowed down by 100 milliseconds per search, and the number of searches per day dropped by 0.2%. And from there, they started doing tests where they increased the latency response to 400 milliseconds, and searches dropped by 0.6%. And then also that effect had, if you kept it at that response time, the searches were down consistently for like weeks. So you want to make sure you're having both a fast and like responsive user experience, and you want to be able to make sure the infrastructure that your software developers are building on top of to build these cool applications, that people hopefully love, they are, we're not the problem, right? We want it to be like, oh, this is bad link color or something, not everything's slow or capacity. Some kind of like classic, I guess, Google examples of those 10 things is if you look at like hard disks, if we buy a ton of hard disks, as you imagine, just when we have like exabytes worth of data. So if you buy a hard disk, it has a mean time between failures of 3 years, and even if you only have 10,000 of these, which I guarantee you we have more of, you can expect 9 to fail every day, right? So just imagine like, there's a very high possibility that I'm going to be saving data to a hard drive that's going to fail today. Or I'm going to be saving data to a hard drive that will not be there tomorrow. And this, you start thinking about like, well then I need to like write to multiple places and things like that. And we design all of our software to deal with these large or small component failures. For instance, if you use Google, and you saw when like Sandy hit New York, that was a pretty significant event for us because, like I said before, most transatlantic cables land in New York. So that, like, if your city's underwater that does most of your like cabling to get across to Europe, there's a very high possibility that you're going to start dropping connections. And so there's sort of, you have to like put in that paranoia, like what happens if we don't have ways to get the data to users? Well, we can start funneling everyone over the Pacific, or we can start we can start paying people shit tons of money to like go to these data centers and make sure they still have gas because there's no power network anymore. Oh hey, someone decided to dig on this like random stretch in the middle of nowhere, and look, we now have a cut fiber, and like we're losing like 14% of capacity to Atlanta. Those are sort of things like you have to be prepared, or at least be able to know, at least be able to know that that's happening, and then be prepared for that to happen. Which kind of comes back to what I've been trying to preach throughout this, which is like monitor everything always, constantly. And so I get to the Google SRE motto: hope is not a strategy. The future. So I guess this becomes like sort of a product pitch now. I work on Compute Engine, which is Google's VMs in the cloud solution, and that is a subset of Google Cloud Platform, which is this very strange cloud on a platform. So in the cloud world, there's basically like 3 classes. There's software as a service, which is a whole other can of worms. But there's also infrastructure as a service, or IaaS, or platform as a service, PaaS. IaaS is kind of your traditional. That's what when people say EC2, that's an IaaS. OpenStack Nova is their compute cloud thing, and Google Compute Engine is our solution to that. And that is like, run a command, and I'll give you a server you can SSH into. It's usually running like Red Hat or Debian or something. Microsoft and Amazon both have, you can also run Windows servers, but for the most part, Linux servers, because Linux is better. And you SSH into it, you run your binaries, you set up some network paths, and ta-da, you have traffic coming from the internet. When you hit an IP, it goes to the server, and the server does things and sends it back. Platform as a service is a little different. The 2 big ones are Google App Engine and Heroku. It's kind of you give them your code, and they try to scale it. Heroku follows a very simple approach. You go to a website or run a command, and you scale from 1 to X, where the larger X is, the more amount of money you pay them, and the larger number of processes you have. App Engine tries to like look at your growth, the number of QPS you're getting in your like incoming traffic, and scale appropriately. Yes, they both have their